Here's the first FRQ for the progress check. We have here a rod that lies on the x-axis for this xy coordinate plane. It has some linear charge density, lambda naught, and we're going to be looking at 2 points of interest. We have point A, that is a distance lowercase a away from the end of the rod, and we have point B that is also the same distance from the rod, but it's underneath the rod and it's at the midpoint. So for the first question, we have to derive an expression for the magnitude of the electric field at point A in terms of L, A, lambda naught, and physical constants. What you want to do for this one, I would say for all of these problems, whether or not you're using Gauss's law or you're just integrating for a charge distribution, that's the tricky part, is doing an integral for a charge distribution, whether or not it's a sheet or a rod or a sphere or a ring, doesn't matter. It's all about setting up the integral. So with setting up the integral, I think first step, you want to figure out what your bounds of integration are. And then you need to figure out how you're going to tackle the problem. And it's one of those things where you simply just have to get more comfortable with doing it by just doing plenty of examples and seeing all kinds of different cases. So not only, from this video, but also from the packets. There's the example FRQs, and then there's that practice test as an additional resource that I gave. So you want to be able to do this one and then go through many more. Let's just start with this one, though. Here, we're going to figure out what the electric field is at point A, and I'm going to take the definition of the electric field for some charge distribution, right? So given that we have a distribution of charge, I have these infinitesimal charge elements, dq, and what I need to do is I need to write dq in terms of the charge density, right? So this has a uniform charge density, right, along the length of the rod. And we're going to use x as our coordinate because this rod lies on the x-axis. Now the hard part is figuring out what our bounds of integration are. So what I'm going to do is I'm going to integrate from this side of the rod all the way from this side of the rod. We're going to integrate from this coordinate in which lies in a position that's at negative x, and we're going to integrate all the way over here. So one thing I want to mention, so why do we integrate from left to right? Why don't we do right to left? Now you can totally do that, but you just have to understand, like, so if I have some function, right, and I'm performing an integral, so you have an xy and I have some arbitrary function, you can totally do it from right to left if you wanted to, right? So say I have positions A and B, but you just have to be careful with evaluating your integral, right? So if I have some integral of some function f of x, well, I know that I'm going to take the result of that integral, I'm going to plug in the upper bound, and I'm going to subtract from it the lower bound. I could integrate from b to a, right? But then when I do the math, I'm going to see that because I'm going from right to left, then I'm going to end up with the negative. But ultimately, you get the same result, right? Because I'd be integrating from the, my lower bound would be b, my upper bound would be a. So what I'm trying to say is, you just use the normal conventions, right? So we're going to integrate from the left to the rod to the right of the rod, because that's how we set up our coordinate system. And now we need to figure out what our bounds of integration are going to be, all right? So we're going to integrate from when x is at this position, right? So at this position, x equals negative L over 2, to this position, x is equal to L over 2, right? As stated, this rod has a length of L, and we have this coordinate system. The middle of the rod sits at x equals 0. So these are our coordinates. This is what we're going to be integrating from. So negative L over 2 to L over 2. Okay? And then I'll plug in the 1 over 4 pi epsilon naught. All right. And then we have our dq. So our dq is going to be the linear charge density. It's a constant linear charge density. It's not a function. It's just a constant value. Right? And also, just to clarify, so whenever you see lambda, all right, that's going to be a linear charge density measured in coulombs per meter. All right, and then if you have a surface charge, they're going to use sigma, coulombs per meter squared. And then if you have volumetric charge density, then it's going to be coulombs per meter cubed. And it's the same symbols that were used when we talked about non-uniform mass distributions, right? So if you have, or just talking about mass distributions in general, you could have a linear mass density or a surface mass density or well, just normal density, right? Kilograms per meter cubed. It's the same concept in electricity, right? Instead of kilograms, we're talking about coulombs. So anyways, almost done setting up the integral. Now we have to write down a value for r squared, okay? But we have to write it in terms of x. So how are we going to do that? Well, if I look at, here, let me use a different color. So we're looking at point A. We have electric field that's going to be emanating out from this rod, all right? And what I'm going to do is I'm going to integrate the contribution of each element. So I'm going to have each element dq here. I'm going to sweep across the entire rod. So for this very first infinitesimal slice of the rod that has some infinitesimal charge, dq, well, this distance here is the r, right? And that distance is simply a. So I know that when x, so right now what I'm doing is I'm kind of reasoning about the bounds. So when x equals negative L over 2, I know that r has to be equal to a, all right? And when x is equal to positive L over 2, right, let's think about it here. So from here to point A, well, I have the entire length of the rod plus a. Okay? And the only function that I can write that satisfies these conditions, okay, is r is equal to a plus L over 2 plus x. And we can check. So let's plug in x is equal to negative L over 2. We see we have negative L over 2 plus L over 2. Okay, that's 0. And then so is my first infinitesimal charge, is it a distance a from the point that I'm analyzing? And yeah, well, that's a yes. And then when x equals positive L over 2, right, and then I add L over 2 to it, I get a distance of L, the length of the rod, plus a. And so it satisfies these conditions. This is what I'm going to be plugging in for my r. That's the distance. That's a function that describes the distance of every single tiny charge element as I integrate across this rod. So I have a plus L over 2 plus x. And again, if this seems a little confusing, all right, you just got to practice. You're going to see all kinds of various scenarios, and you have to get into the habit of setting up your bounds of integrations, checking with the guide, see what the solutions say, and just develop this intuition for how to set up your integrals. That's the hard part. And once you've set up your integral, well, the calculus isn't all that bad. So actually evaluating the integral, it's not too difficult. So here, what I'm going to do in terms of like showing the steps, because if you look at the solution guide after you submit your FRQs, they kind of just skip around on the steps. So here, I know that all of these values are constant. The 1 over 4 pi epsilon naught, the lambda naught, a, L over 2, these are all just constant values. What we really care about is the x, okay? Because we're integrating with respect to x, and we have this dx term. All right, so basically I have a 1 over x squared in a denominator. So off to the side, I'm just going to do the indefinite integral of 1 over x squared, okay? And when you integrate 1 over x squared, right, it's the same thing as x to the negative 2. So remember the power rule, and you should end up with negative 1 over x. Okay, that's the answer to the indefinite integral. All right, so then what we need to do is we need to actually evaluate this integral. All right, so I'm going to pull out all the constants. I got my 1 over 4 pi epsilon naught. Let's see, what else we got? Lambda naught times lambda naught. And that's pretty much it. Yeah, I can write this as lambda naught over 4 pi epsilon naught. And then we know that the integral of 1 over x squared is negative 1 over x. So I have negative 1 over a plus L over 2 plus x. in the denominator, and I'm going to evaluate that from negative L over 2 to L over 2. All right. So at this point, what we need to do is just plug in the values, right? So I'm going to insert my value. Here, I'll drop this off to the side. So now let's evaluate this part, right? I don't want to have to rewrite the coefficients every single time. So I'm just going to kind of just look at the evaluation here. And then when x is equal to L over 2, I have negative 1 over A. I'm sorry. You want to do the upper bound first, and then you subtract from it the lower bound, right? So let's so plugging in x equals L over 2, I have L over 2 plus L over 2, which is L, plus A. So I have negative 1 over A plus L. And then I have to subtract my lower bound. And when I plug in my lower bound, I get negative 1 over A. So effectively, I have negative 1 A plus L plus 1 over A. All right, and now I need to get these to have a common denominator. All right, so the way I'm going to get this to have a common denominator, I need to turn this A into an A plus L. All right, so, well, in order to get an A plus L, right, what I need to do is I need to multiply this by, so here, let's get the common denominator set up. So what I'm going to need to do is I'm going to need to multiply this by 1 plus L over A over 1 plus L over A. All right, and when I finally evaluate this, well, let's look at the denominators, right? So I have A times 1, which is just A, plus L over A times A, which is just L, and then there you go. That's how I end up having the same common denominator. So I have 1 plus L over A divided by A plus L. All right, so that's how I'm going to get common denominators. And then I'm going to add these together. So I have negative 1 over A plus L plus 1 plus L over A all divided by A plus L. Okay? And then, well, I have, and let's add the numerators together now. They have common denominators. Negative 1 plus 1 is, well, 0. All right, so I have L over A. So L over A divided by A plus L. Right? And that's the same thing as, so I have L over A plus L. That's the same thing as L over A times A plus L. Right? And now I'm going to bring back my constants. So notice I put this all in blue because I'm only looking at the evaluation. So don't forget, whenever you're trying to save space and doing your calculation in parts, you just got to, keep in mind what you're doing. So here I'm going to write down my final expression for the electric field. So my electric field at position A is going to be equal to lambda naught times L, right, divided by 4 pi epsilon naught times A plus L. All right. So that's my final answer for the first one. All right, now the next one. Write, but do not solve. All right, so something you want to watch out for. If you ever see this, write, but do not solve, that means the answer is a particularly nasty integral because they don't want you, this isn't testing you on whether or not you've memorized all the little trigonometric integrals and all the little tricks to integrate these more complicated functions. The whole point is to demonstrate your understanding of physics, right? At the end of the day, you can just plug it into a math program and to evaluate the integral when you have a particularly tricky one. But so I'm not going to bother solving it. I'll show you what the solution looks like. But you'll see that it's not worth the time. So again, when you see write but do not solve, right, you just need to write down the integral and then that's it. With the correct limits that could be solved to determine the magnitude of EB, the electric field at point B, and we have to express our answer. All right, so now for point B, okay, what we want to do is So I'm doing the same thing. I'm going to sweep across the rod, okay, except now it's going to be like at an angle, right? So here I have some electric field from this little infinitesimal piece of charge on this rod, and it's going to be generating a field. So the field, how the field is going to be affecting this point, right? I'm going to have some field going this way. And then when I go across the rod, right, I go from the middle, it's going to be going down this way, and then I have this little element here. All right, what we should notice is that the horizontal components are going to cancel out, right? So I have some electric field. The electric field that exists at point B from the left side of the rod is going to be pointing down and to the right. All right, assuming this is a positively charged. Does it say it's positive? All right, we're just going to assume it's a positively charged rod. So this one's going to be going down and to the right. And then when we look at the little infinitesimal piece of charge in the middle, that's going to be generating a field that's going straight down. And then obviously on the right-hand side, it'll be generating a field going on the left-hand side. So what's key about this is that the things that add, right, so the actual components of the electric field that add together, all right, are the components, like the horizontal components are going to cancel out. And then it's the components that are going to be pointing down. So the parts of each piece of the infinitesimal charge that's pointing downward, that's going to be contributing to the total electric field at point B. All right, so let's set it up same way we set up point A. All right, I'm going to write it off to the side here. So this is for part 2 for this problem. So again, set up the same integral. So the electric field at point B is the integral of 1 over 4 pi epsilon naught times dq over r squared. All right, and then the same thing as we did before. dq is equal to lambda naught times dx, right? And there's no function for lambda naught, it's just a constant. It's a uniform density. And then here, what we need to do, we got to set up our bounds again. So again, we're integrating from when x is equal to negative L over 2 to L over 2. Okay? So we have here the electric field at point B is equal to integral from negative L over 2 to L over 2, okay, of lambda naught dx, all divided by a squared plus x squared. Now, why is it a squared plus x squared? Well, let's think. Like we did last time, we looked at our bounds of integration, and we saw, okay, so what is the actual distance of each little infinitesimal piece of charge element? So here, we saw the distance was consistently increasing when we did part 1. We looked at the electric field for A. Here, the distance starts off as far away as it can be from here, from the point B. Then it goes to the middle, where it's a distance A away, right, at x equals 0. And then here, at the edge, it's going to be a distance, again, it's going to be the diagonal distance, this distance from here to here. So I have a height of A, okay, and then my horizontal distance is x, is a function x, so it goes ranging from negative L over 2 to L over 2. So it's basically just a Pythagorean theorem, right? So the distance for each infinitesimal charge element, okay, you're going to use the Pythagorean theorem to see how far away it is from point B. Point B, so it's like every single little piece, every time I look at a little piece of the rod, okay, it's going to form a right triangle with a height of A, and the base is going to be x, all right? So that's why we have this formula over here. If you looked at our previous problem, we saw we had this A plus L over 2 plus x, and here we have A squared plus x squared, okay? And then last bit that's important, okay, is, like I was saying, it's a component of the electric field that's going to be adding up, all right? So the components that are pointing in this direction, they're going to cancel out. Only the components that are pointing down are going to be adding up, all right? So here, we're going to define theta as this angle over here. Now, you could choose a different angle. You could choose this angle, and then you'd have a different trigonometric function, but it's all going to turn out to be the same anyways. And hopefully you'll see it as we work through the problem. But here, if I use this angle, theta, all right, well, the component that are going to be adding up as I integrate across this entire rod, that's going to be we're going to have to use cosine for that one, right? Because if I keep forming right triangles, it's going to be the adjacent side of the component that's going to be adding up. So I have to multiply all this by cosine of theta, all right? But the thing is, we're integrating with respect to x. So I have to write cosine of theta in terms of the values that I'm given, right? So let's imagine I take some little charge element over here at the edge. Okay, so I have this little piece of charge, and then I'm looking at point B. All right, well, it starts off some distance x from the center, right? Technically, it's going to be at x equals negative L over 2. Okay, and then here, the height is going to be that distance a. All right, so now x is going to range from negative L over 2 to positive L over 2, but regardless, if I want to figure out this distance over here, how far away that little infinitesimal charge element is from my point B, all right, well, I had to use Pythagorean theorem. So it's just x squared plus a squared. But then also in terms of like the component that of the electric field that actually adds up across the entire rod, well, that component there, I guess it might be easier just to see it. It's basically this distance a away from it. So if I do here my lambda, so I'm looking at this component that's parallel to a, that's going to be the component of the electric field that's going to add up as I integrate across the entire rod. Well, if I choose this angle theta here, well, that component is going to be adjacent over hypotenuse, right? So if I choose this angle theta here, cosine theta, well, I know I can't integrate it with respect to theta, right? I have to write it in terms of x and physical constants. So cosine of theta, the adjacent side is a, and then here we have the hypotenuse, right, which is going to be a squared plus x squared. Okay, so now I'm going to substitute that in. I'm kind of running low on space here, so I'm going to move on to this little section here. So this is part 2 continued. Alrighty, so now at this point, what I'm going to do, I'm going to replace that cosine theta with this expression, the a over a squared plus x squared. All right, and here I have my electric field at point B is equal to the integral of negative L over 2 to L over 2 of lambda naught dx over a squared plus x squared, okay, times the cosine of theta. But we already said that the cosine of theta has to be this, a divided by the square root of a squared plus x squared. Now let me go back to talk about this little phi. So why did we choose that? Why didn't we choose a different angle? Why did we have to use cosine? Why not use sine? Now you can do that, but you just got to be careful, right? So I mean, ultimately you're going to end up with the same answer, right? If I look at the sine of that angle here, I'm going to call this angle phi. Okay, well, we have to look at the component that is parallel to where the electric fields for each little charge element are going to be combining together, right? And so in this case, we would use sine for this angle, and that's going to be opposite over hypotenuse. You still end up with the same ratio. So that's the thing. You're gonna end up with the same ratio of this a over the square root of a squared plus x squared. So ultimately, it doesn't matter. So now we have to simplify. And keep in mind, we're just setting up the integral. So we're writing, but we're not solving the integral, because it turns out to be a pretty nasty trigonometric integral. Yeah, it's not too bad. You got to do some substitutions, but it's tedious. So here we end up with, so I have a squared plus x squared in the denominator, and then I have basically, well, square root is just a squared plus x squared raised to the 1/2, right? So when I multiply these together, what I end up with is EB is equal to the integral from negative L over 2 to L over 2 times lambda naught A dx all over x squared plus a squared to the 3/2. All right, so that's my answer. Whereas like a squared plus x squared in the denominator. You get the idea. Alrighty, so now the original rod is replaced with a new rod of the same length, same diameter, same total charge density of the original rod. However, the new rod has non-uniform charge density modeled by lambda sub x, or lambda of x is equal to beta times L over 2 plus x. All right, so now how does the new electric field at point A due to the rod compared to the magnitude of the electric field derived in part A1? Justify response. All right, so I think the easiest way to think about this is, well, let's think about how the charge is distributed, right? So for the first rod, it was uniformly distributed, right? So I can even like draw a little plot of the original charge distribution with respect to x, and we saw it was a continuous charge distribution. Now it has the same charge, except we're just shifting some of the charge to the right. All right, so now we have this new charge distribution where at the very left end of the rod, there's no charge on it, right? So if I plug in x equals negative L over 2, I end up with a charge distribution on the left-hand side of the rod being equaling 0. And then it's going to increase as we go across x. All right. However, the total charge has to be the same for both. So then the question is, if we look at this new charge distribution, like here's how I physically think about it. So I'm going to draw a rod. There's like no charge on the left-hand side, and then the charge builds up on the right-hand side, okay, until we have a lot more charge on the right-hand side than on the left-hand side. And the idea is the electric field has to actually be less, okay? So for the E nu, right, so we know that E nu is less than the electric field contribution in part 1, right, part A1. And the justification for this is basically as I integrate across this rod, right, the total charge remains the same, but now more of the charge is further away from the point B, right? Because here it was totally symmetric across the y-axis, okay? And basically, I'm going to have more of the charge on the right-hand side, which is further away from point B than in the original distribution. And keep in mind that the total charge remains the same. All right, so now I have more charge on the right-hand side that's going to be further away, so therefore the electric field is going to be smaller, right? So hopefully that makes sense, right? This has to do with the definition of the electric field and how we derive it from this equation, or at least how we use it from this equation here. And basically, since R is going to increase while keeping everything else constant, the total electric field is going to be less. So the new finite rod is replaced by an infinitely long line of uniform linear charge density. Okay, and now we have to derive it for the infinitely long rod. All right, so anyways, what we need to do is we actually have to use Gauss's law. All right, so let's set up Gauss's law for part B. Let's see here. All right, so now we have Gauss's law. All right, so the electric flux around a surface, so around some Gaussian surface, that has to equal the charge inside that surface divided by epsilon naught. All right, so here I have an infinitely long piece of rod. I'm just going to construct a Gaussian surface. I'm going to construct a cylinder. And the reason we construct a cylinder is because the cylinder, the walls of the cylinder are going to be perpendicular to electric field lines, right? So if I have an infinitely long wire, all right, the electric field lines are going to be pointed up and down, right, if I have a positive wire. All right, so above the wire, the electric field is pointing straight up. Below the wire, the electric field is pointing straight down. So I have to use the cylinder, right? So this little horizontal cylinder, to be able to apply Gauss's law. All right, so now it's the same kind of process of what we did before. Now, actually, let me draw this a little bit bigger. So I'm going to draw a slightly larger cylinder. Okay, so now we're evaluating it at position, at point B. So at point B, all right, so here's point B. It's a distance A away from the line. And then we know that this area, so the area of the walls of the cylinder, all right, is going to be basically the circumference of the circle times the length of the cylinder. All right, so I'm just going to use this little symbol L to represent the length of our Gaussian surface. All right, we're not defining what the length exactly is, but I'm just writing down a little variable to show basically how long the cylinder is. All right, so the area of the walls of the cylinder, we have 2 pi r times L. All right, so now when I set up Gauss's law, all right, I know that the charge distribution times L, okay, that's going to equal the charge enclosed in the cylinder. All right, so I have some charge distribution of this wire, and if I look at a certain length of the wire, all right, I want to see how much charge is enclosed in that piece of wire. Well, I just take the charge density times how long that piece of wire is, and that tells me the total charge. All right, so now we can plug this in to Gauss's law, and what we end up with is E is equal to lambda naught times L, all divided by, so here I'm looking at this equation, Gauss's law. All right, so E times dA is equal to Qn over epsilon naught. All right, so let me I want to write one step down at a time just so we're clear on what's going on. So the area of our Gaussian surface is 2 pi r times L, and that has to equal the charge inside. All right, so we just said that the charge inside is going to be lambda times L. All right, so I have lambda naught times L over epsilon naught. All right, and notice here that the L's are going to cancel out. And what we have here, I'm going to go back to this side. So the L's are going to end up canceling out. Oops. Let me do that. And then we have lambda naught divided by 2 pi a times epsilon naught. And that's going to be our answer. All right. So now let's move on to the next one. So here we have some sphere with some charge inside the sphere, and we have these shells of conductors, these little concentric circles of shells and conductor lying within the sphere, and we're basically going to determine what the electric field is at these distances. Okay, so here we have a plot that tells us the electric field strength. Okay, so if we look at each of these boxes, oh, whoops, I got to set up the edit PDF. All right, markup. So if I look at these boxes here, they're all subdivided by 3's, right? So I have 2r over 3, r over 3. This is going to be 4r over 3, and you get the idea. All right, so now it tells us the electric field strength. This is kind of working backwards from the example that we gave in class, right? So typically you figure out what the charges have to be on the sphere, and then you can sketch the electric field. But now what we have to do, working backwards, we have the values for the electric field at these different points, all right? And then we have to figure out, what's part I say? So we have to draw arrows to indicate the direction of the electric field, and then later we're going to have to figure out how much charge is on different parts of the sphere. Okay, so anyways, we have the point charge in the middle, and then we have 2 layers of conductors, okay? So here, the point charge in the middle, well, a positive point charge emits electric field radially in all directions. All right, so here I have some electric field over here, and then some electric field over here, and then over here it's going to be pointing this direction. All right, and then for the electric field that is in between the two conductors, what we find is that the electric field has to be 0. All right, so the electric field here, it asks us to write E equals 0 whenever possible. And then finally here, we know that the outside shell of radius 2r, where does it say? So we know the charge on the shells are unknown. But if we look at our value for the E field, well, we know that it has to be 0 within the conductor because that's what it tells us in the graph, right? So the E field has to be 0 here between R and 2R, all right? So we're between R and 2R, we see the E field 0. But then as soon as we approach here, all right, a distance 3R apart, here, what do we have here? We have 6R over 3, so we have 7R over 3, 8R over 3. All right, and I'm just plotting all the values on the X, on the, well, I guess the R axis. So now what we need to do is we have to look at this region, all right? And that's where the region for these dots is at some distance greater than 2R. So I'm looking at these different distances greater than 2R, and I see that the electric field strength is negative. So if the electric field strength is negative, as soon as I go past the conductor, right? So we know that the electric field, okay, around the conductor, well, it depends on the charge enclosed, right? So if I have a negative field, okay, radially outward is going to be positive, radially inward is going to be negative. All right, so these are my electric fields for, or at least the direction. We don't need to figure out the magnitude. We'll figure that out. At least we'll figure out the magnitude of the charges in the next problem. But as long as you got the direction, so we have radially inward, radially outward for this system. So now for part B, we have to derive an expression for the net charge on the outermost shell in terms of Q. All right, now for this one, well, we have to use our values for the electric field to figure out how much charge is inside. So we're going to construct these Gaussian surfaces, okay? So within the conductor, before the first layer of the conductor, well, the charge enclosed in our Gaussian surface, right? So if I construct a Gaussian surface, all right, well, the charge enclosed is just positive Q, right? So at R is equal to, all right, so at R is equal to R naught, okay? We know that that's at a radius of, well, we have to relate the electric field strength to the charge inside. So here's the thing, this E naught, okay? This E naught is not the electric field strength when it's some radius capital R away from the point charge. That's what makes this slightly annoying. So it's when the distance from the charge is 2R over 3. So we have to use that fact. All right, so we know that, where am I organizing all the work? Oh, over here. So at R equals R naught, right? We know that's at a distance 2/3 R. So 2/3 capital R, all right? And we know that the charge enclosed has to be positive Q. Well, we're going to be using Gauss's law, all right? So we created our Gaussian surface. Then we know that has to equal the Q inside divided by epsilon naught. Okay, well, the area of our Gaussian surface is going to be, well, we have the electric field strength, E naught times 4 pi R naught squared. That has to equal the charge inside divided by epsilon naught. All right, so this charge, positive Q, has to equal 4 pi epsilon naught squared, R naught squared, times E naught. Right, and all I did is solve for Q. I just multiplied both sides by epsilon naught. All right, so now, ultimately what we're trying to figure out is the charge on just the outermost sphere. Yeah, the net charge on the outermost sphere in terms of Q. All right, so I'm constructing my Gaussian surfaces, and I'm trying to see how the charge is distributed. Well, I know the E field after this conductor, right? So this shell here is a conductor. The E field in between the two conductors, right? So these two shells, it ends up being 0. Now, the only way for that to be possible is if I have some E field. So I have this E field pointing out from the positive point charge, right? So I have to have E field that's pointing inward with the same magnitude in order to cancel out the E field with the electric field from the positive point charge. So that means I have to have a negative Q distributed across this entire sphere, right? Because that's the only way. If I construct a Gaussian surface, so I'm going to construct another Gaussian surface in this region, right? Here's my new Gaussian surface. Well, if the strength of the electric field is 0 around this Gaussian surface, then the total charge inside the surface has to be 0, right? And that's the rationale. So here we have at R, right? So at R is equal to 5R over 3. All right, so again, we're deriving an expression. So as R increases, all right, well, I know that the charge inside at R equals 5R over 3. We know what the electric field strength is. We know the electric field strength has to be 0. Okay, so that means that the enclosed charge has to be equal to 0. All right, and the only way for that to be possible is if I have a charge of negative Q on this first conductor. Right? So that's the rationale. So I know that Q, so the Q for this Gaussian surface, right, within this Gaussian surface, I'm sorry, the Q of this conductor has to be equal to the negative charge of the point mass, or the point charge in the middle. All right, so hopefully this makes sense. So I'm looking at the E field. I know Gauss's law, right? E times the integral of EdA is equal to the charge inside divided by epsilon naught. All right, so if the E field is 0, that means the charge within the container has to be 0. So within this Gaussian surface I just drew in blue. All right, so that means that this conductor has to have a total charge of negative Q in order to cancel out with the charge of positive Q to meet the condition that the E field is 0 in between these two conductors. All right, so now that I know these two facts, what we can do is we can finally solve for the amount of charge that has to be on the outermost conductor. All right, so at R is equal to 8R over 3. Okay, we know that the electric field strength, so here I'm writing everything in terms of the initial radius, right? So my initial radius, R naught, all right, is 2R over 3. Okay, so then here, I know that the radius is going to be, let's see, what does that come out to? 2.5 times as much. But it turns out not to really matter all that much in the sense that, well, the charge inside ended up being 0, right? In this case, we know the electric field is 0. But that's what I meant when I wrote this down. So at R equals 5R over 3, okay? Well, we know that it's that much further away from the center than the point charge. But now here, this is where it's going to become relevant. So now the electric field at this position is negative E naught, and that's how we're going to use to determine the charge on the outermost conductor, right? So that's 4 times the distance. So we're going to make a Gaussian surface that's 4 times the distance from our first Gaussian surface. Right, so I'm going to draw another Gaussian surface out here. All right, so I'm constructing another Gaussian surface. And I know the total charge within these two has to be 0. Okay, so now we just need to figure out the total charge on the outermost conductor. All right, so what I'm going to write down is, so let's see here, what do we have? So at a distance 8 capital R over 3. All right, we know that's 4 times the original distance for the original Gaussian surface. All right, and now I'm just going to plug these values in. So I know that the electric field strength is negative E naught. I know that the area of this new Gaussian surface is 4 pi times 4 R naught quantity squared. All right, and then that has to equal the charge inside divided by epsilon naught. Well, I know that's a charge within this conductor, and I just drew in red. Okay, so, and this Gaussian surface we just went over, all right, that total charge is 0. So now I'm only going to be looking at the charge on the outermost edge. All right, so that has to equal, we're going to call that Q2, the charge on the second conductor, divided by epsilon naught. All right, and then when you crunch the numbers, I have 4 R naught. So when I'm 4 times as far away, okay, from the center, all right, then the strength of the E field has to be negative E naught. All right, we need to figure out what total charge has to exist. So if I have 4 R naught squared times 4 pi, right, we have, well, 4 squared is 16 times 4, then we end up with 64. So Q2 is equal to negative 64 times pi times epsilon naught times R naught squared. All right, times E naught. All right, so we had to, in terms of Q, all right, so in terms of Q, well, I know that positive Q, right, has to equal 4 pi epsilon naught R naught squared times E. That's what we just wrote down earlier, right? So this here is the value of Q, all right? And then we're going to figure out how much charge is on the outermost shell. Well, let's look. So how many times is 64? Like, all the other terms are the same. How many times is 64 bigger than 4, right? So we know that has to be 16 times as large, right? So my electric field around this outermost conductor, okay, it's going to be 16 times as large, but it's not, it has to be negative. So notice that we have an E field that's pointing radially inward. All right, so that means that the charge over here on this outermost conductor, right, just crunching the numbers, we know it has to be equal to negative 16Q, right? So I'm going to call this Q2, and it has to be negative 16Q. All right, and then that's my answer. So here we have, let's see, so we have negative 16Q and all the work shown above. And we drew our electric field strengths. So now we have to sketch the electric field as a function of R as shown in figure 2 from R equals 0 to R equals, or from R is greater than 2R. All right, so let's sketch the electric field. I know that the electric field around the point charge has to follow an inverse square law. All right. So here, when I'm halfway, so here's the idea. We know it's proportional to 1 over R squared. All right, so at R over 3, that's halfway in between 2R over 3 and 0, right? So because of the inverse square law, I know that the electric field decays following the inverse square law. So I know at this position here, the electric field has to be up there, all right? And it's going to decay as I move further and further away from the point charge until it eventually reaches 0. So that's going to happen at this radius, right? So once I reach this conducting sphere with a radius of R, okay, I know that the charge on this sphere has to be negative Q, and the electric field drops down to 0. So at this position here, the electric field has to drop down to 0, and it's going to stay 0 until it reaches a distance of 2R away from the center. So from here to here, it's 0. Here, it's just a decaying inverse square law. And then here, right, once we move past the boundary for the second conductor, okay, it is going to follow, and again, we're just sketching here. So then it's going to follow an inverse square law, right? But again, it's going to be coming in from this direction. All right, so that's my sketch. Again, so it's inverse square law. So that's what it turns out to be. All right, so now let's move on. Oh, wait, I got to hit done. So here we have to, all right, so this is another lab experiment. And we're studying Coulomb's law, right? So the attraction or repulsion felt by spheres. So here we have two identical conducting spheres, each with a positive charge. Sphere 1's attached to insulating stand, and sphere 2 is suspended from a ideal non-conducting string. The spheres are briefly brought together in contact and separated, after which they have the same net charge. So you have to design experimental procedure that can be used to create linear graphs to determine the charge in each sphere. For enough detail, the experiment can be replicated. So there's two different types, right? So when you end up looking at the scoring guidelines, there's two different ways. Actually, there's multiple ways to set up the experiment, but there's two examples that they give. Oh, wait, did I just skip one? Oh, shoot. Yeah, I did. So suppose if any charge, if any, was made on the outermost shell is removed, making the outer shell electrically neutral, what changes, if any, would be made to the graph you drew in part C? All right, so I forgot about part D. Well, anyways, oh, no, I deleted it. All right, so you saw how I had an inverse square law. All right, if the outermost charge in the outermost shell is 0, well, then the electric field is going to be 0, right? Because we know that within the first conductor and the second conductor, the electric field is 0. And the only reason there's electric field outside of that is because we figured out that the outermost shell has a charge of negative 16Q. And if I remove all that charge, well, then the total charge within the system is just going to be 0. So there's going to be no more electric field outside of the conductor. All right, so anyways, going back to this. So I'll just briefly go over, because, I need to kind of wrap this up. I spent a lot of time on the very first problem. So I'm just going to kind of run through this quickly, and then we can get to the last one. So here's basically how I thought about the experiment. All right, and I'm just going to read. I'm not going to write it out. All right, so what we do is we have, so I should do a drawing. Oh, shoot. So I should do a drawing just so we understand what's going on. So basically we have this insulating stand with a sphere on it, okay? The sphere is just sitting there, all right? And we have another sphere that's attached to a string, all right? Very long string that's dangling from the ceiling. Okay, so that's strings attached to insulating stand, suspended from an ideal non-conducting string. All right, so basically what makes the most sense, at least to me, is what we're going to do is I'm going to bring this conducting sphere close to this other charged sphere. So I have two charged spheres. All right, actually I can make it a little bit more obvious. All right, so they're going to start far away apart. And then I'm going to bring them closer together. All right, and as they get closer together, then this sphere is going to be repelled because of the electrostatic force. And then basically we have to figure out how much is it repelled by effectively measuring the angle. So I'm just going to read through the procedure. So effectively measure the angle of sphere 2, right? And we're going to... All right, so we're going to figure out the angle sphere 2 makes with the vertical as sphere 1 approaches it by measuring the length of the string and how far sphere 2 displaces from sphere 1 as sphere 1's brought closer to it, okay? All right, so as sphere 1's brought closer to sphere 2 is going to displace some amount from its equilibrium. And then if I do some trig, I can figure out basically what the angle is, and then I can figure out what the electrostatic force is by looking at a free body diagram. So I look at a free body diagram, and I have some tension going up in this direction. I have some electrostatic force here, and then I have the weight of the sphere 2. So then we're going to measure the distance between the center masses of the spheres using a meter stick, and we're going to be bringing sphere 1 closer and closer to it to see if it follows Coulomb's law. And then if it follows Coulomb's law, based on the mass of the sphere and how much is deflected from equilibrium, you can figure out the charge on the spheres. So we know that the spheres have to have the same charge, right? Because the spheres are briefly brought into contact and separated. All right. So we know they're going to have equal charge. All right, describe how data can be used to produce a linear graph and how the graph will be analyzed to determine the charge in each sphere, right? So let's just go over the equations. So I have F equals K Q1 Q2 over R squared. All right, and I know that Q1 has to equal Q2 because these two spheres are, they touch before they're separated. All right, so I'm just going to write Q representing the charge on each sphere because they're both going to be the same. So we have K Q squared over R squared. That's going to be my force. And then I'm just going to kind of run through. Wait, does it go over? All right, this is a different experiment. All right, so I drew a free body diagram. Let's go back to our free body diagram and let's analyze the forces. All right, so the angle that the tension makes with respect to the vertical, all right, it's going to be this angle here. And then we know it's going to be in equilibrium because as you bring it closer, right, the second ball is going to be pushed away, but it's going to be, staying at rest. So we know that if I look at these components here, I know that T times the cosine of theta, that has to equal the force of gravity, right? That's just the weight of the sphere 2. And then this component that is should be equal to the electric force, right? So this component here, T sine theta, has to equal the electric force, which you said was K Q squared over R squared. And then what we need to do is we need to relate how far away sphere 2 is displaced from equilibrium with respect to how close sphere 1 is to it. All right. So what we can do is we want to ignore the tension, so we have to cancel them out some way. So I'm just going to divide these two equations, right? Or I think what makes more sense is to do T sine theta divided by T cosine theta. All right, and we know that has to equal K Q squared over R squared, but then all that divided by mg, so I have over R squared times mg. All right, and then for this experiment, what we'll do is we're changing the distance between the spheres, so that's our independent. Our dependent is the angle, effectively, for the sphere that's hanging from the ceiling, right? And here, this has to equal tan theta. I forgot to mention that. So then in terms of what we could graph, right? Well, I would graph, so if I have tan theta is equal to K Q squared over here's how I'm going to write it, over mg times 1 over r squared, because r squared is our independent, tan theta is our dependent. So that's basically what I would plot, right? So that's our dependent variable, this is our independent variable, and then this is our slope. All right, so I'll put tan theta in the vertical, 1 over r squared in the horizontal. Then my slope's going to equal K Q squared over mg. Then you, something I forgot to mention, I'm not sure if I mentioned it, but for the procedure, at some point you have to weigh the spheres, right? So you have to, well, you don't necessarily need to weigh sphere 1, but you have to find the weight of sphere 2, right? Or know you can also use the balance to find the mass of sphere 2, because you need to know that in order to determine the strength of the electric force. And that's pretty much it, right? And so if you want to figure out, so describe how data could be used to plot a linear graph and how the graph will be analyzed to determine the charges here. All right, so then you plot your linear graph. We know slope is equal to K Q squared over mg, right? So then if I want to figure out Q squared, or the charge on each sphere, right, then I know that Q squared is equal to the slope times mg all divided by K. All right, so that's going to be the how you figure out the charge. And then obviously you take the square root. So it would be the square root of the slope times the weight, that's sphere 2, divided by Coulomb's constant. So here, what quantities could be graphed to yield a straight line? So now we have a constant force, right? So they're going to be changing the charges, they're going to be changing the distance between them. And we know that we're getting a constant force of 3.4. 3.4 newtons. So here on the horizontal axis, well, at this point, what we need to do, all right, is write out an equation. So I have K, Q1, Q2 over R squared. Now this time the Q's are different, all right, but we know that the force has to be a constant. All right, so we're changing R and we're changing Q, and we're trying to figure out what the Coulomb's constant is, right? So for this experiment, the way I think about it is the charges are the independent. So you're changing the charges because the radius, this measured radius, basically you're kind of fine tuning it until the force is 3.6, right? So you're trying, I'm sorry, 3.4. So you're trying to get a force of 3.4, right? So that radius is what you're going to be measuring, right? So you find the point where the force between the spheres is 3.4, and then you measure that radius. So that's going to be our dependent variable. Typically you put that on the vertical axis. So looking at this equation, if we want to solve for K, I'm going to rewrite this. So the product of K1 and K2, that's my independent. Okay, that has to equal, actually let me write it like this. So F times R squared is equal to K times Q1 Q times Q2. Right, so I can kind of rewrite this. I'd put R squared is equal to K over F. Keep in mind that F's the constant in this experiment, times Q1 times Q2. Right, so my dependent is the R squared. My independent is the product of the charges. Right, and again, we'll do the same kind of trick, right? Y equals mx plus b. All right, so on the y-axis, I'll put this. On the x-axis, I'll put this. And then my slope is Coulomb's constant divided by that constant force. And we're going to plot the data points. All right, I'm definitely not going to do that. If you want to see what it's going to look like, we're running low on time. So here's basically what it looks like. And again, this is very important. And I mention this in every video, that there's a lab question. When you're drawing a best fit line, you have to pick points that are on the best fit line. You can't pick data points. Then you determine the slope. You perform the calculations based on how the experiment is set up, and then these are some sample values, right? So you notice there's a bit of wiggle room, right? It depends on what you want to graph. So if we were to graph this, we should get a value about 9.64, and let's finish up this video with the last FRQ. So almost done. This one's also on electrostatics, or I'm sorry, on Coulomb's law, so it's not too bad. So here we have this XY coordinate system, and we have point P, that's d over 2 away from sphere 2. And then these are the coordinates. So point P is located at coordinates positive d over 2, positive d over 2. Okay, because this is where x equals 0. So x equals 0 here. This is my origin, right? So x equals 0 over here. So that's why the coordinates for point P are such. Sphere 1's at this. All right, we get the idea. So we need to draw a arrow representing the direction of the net electric force that be exerted on a positive test charge Q located at point P. All right, well, let's look at it. So I put a positive charge here, right? And then this charge is negative. This sphere is negative. So it's going to attract, right? Opposites attract. So here I'm going to have a large force being pulled into this sphere. And then this sphere, look how much further away this sphere is from point P. All right, so point P, I put a positive test charge here. It's going to be much more, it's going to have a much stronger attraction to sphere 2 and then to sphere 1. All right, so then I have this little force over here. Keep in mind, it's the inverse square law. So I do a vector combination of those two forces. It's not going to be quite 270, but it's going to be in between 225 and 270, but closer to 270, right? So, yeah, that's pretty much it. Right, because we see how much closer sphere 2 is. It's directly beneath the positive test charge. Justify why the force direction indicated, because I did a vector sum of the components, right? So I have these two vectors. I do the vector sum to get the net force on the charge, and it's going to lie between 225 and 270. And you could calculate it if you wanted to, right? Because you have basically a right triangle to figure out what the angle is. And you know that its height is 1/2 of the base of that triangle, right? So you can calculate that angle, but you could calculate the force too. But I just think based on intuition, we should see that sphere 2 is a lot closer, so that force is going to play a much larger role. All right, so we place a positive test charge at coordinate 0y, where y is greater than 0. We have to derive an expression for the force on the test charge. Okay, so here I have a test charge at coordinate 0y. So I'm going to put a positive test charge here, and we need to figure out the electric force acting on the test charge. Is point P a constant? Yes. So that's the distance, right? So from here to here, this is y, all right? And then here I have a force pulling this way, force pulling this way, in terms of the distance between here to here. Oops. All right, so I have d over 2 for the base of the triangle, and then I have y for the height. So this diagonal distance here, right, I'm going to call that r. This is for both spheres, by the way. I have square root of y squared plus d over 2 quantity squared. All right. And now at this point, I think we just need to add the components of the force. All right, so from superposition, we can add these two forces together. All right, and if we think about it, drawing our free body diagram, these horizontal components are going to cancel out. And so I have sphere 1 pulling down and to the left, sphere 2 pulling down and to the right. It's a perfectly symmetric situation. So those horizontal components are going to end up canceling out, and it's going to be the sum of the vertical components for the force. All right. So here I'm just going to write the equation. So since they're both the same charge, sphere 1, sphere 2, I'm just going to write the force for one of them in the vertical direction, right? So pointing in the negative y direction. And then I'm just going to add them up, right? Because there's two forces, one from each charge, right? So I'm going to write, we're just going to do one charge, the force from one charge at a time. So I have k times q, wait, hold on a second. Yeah, so, and again, I'm just going to look at the magnitudes. All right, so we understand a vector has magnitude and direction. We're just looking at the magnitudes. I'm trying to wrap this up rather quickly. All right, so kqq over r squared, where r squared is y squared plus d squared over 4, right? So if I do d over 2 quantity squared, I get d squared over 4. And then so we're going to do the vector sum, and that's going to be this component here. So we have our sum in the y direction, right? So k, q over r squared, and that's r squared is this value here. Actually, yeah. All right, so I'm writing it separate, so we signal that it's the vertical component. So d squared over 4 times the sine of theta. All right, and that's just a contribution of one of the charges. Then I have to write theta. So sine of theta, again, in terms of the ratios. All right, so let's say that this is theta over here. All right, well, the ratio for theta, for sine theta, is opposite over hypotenuse. All right, so sine of theta. Again, we can't do it in terms of theta. Like, why are we doing the definition of sine, cosine, tangent as defined as a ratio? And the reason why is because we have to define it using these values, okay? So I can't just leave sine theta, right? I'm sure you get a decent amount of the points, but you wouldn't get the full credit. So here I have the opposite side, which is y, and then the hypotenuse is y squared plus d squared over 4, square root of that. So I'm going to multiply these two together, right? So if I take this term and I multiply with this term, I'm going to end up with k q over y squared plus d squared over 4 times this denominator, and that's basically going to raise it to 3/2. And then this is the force from one of the charges, right? So we have a symmetric situation, so I just looked at one of the charges. Given that we have two charges, right, and the whole setup for the problem is practically the same, well, then my final answer, right, so I have to do, this is, say, from sphere 1. So that's like the force from sphere 1. The force from sphere 2 is going to be identical. It's just going to be going down and to the right. So we're just adding the vertical components of these forces. And then my final answer is 2kqq over r squared plus d squared over 4. All right. Oh, to the 3/2. I can't forget the 3/2. All right, finally, almost done. So now we have sphere 1 on the left replaced by positive q. Describe how the force magnitude you derived in part B and direction of the force on the test charge would be different, if at all. Justify response. So it would not be different at all, but it would change direction. So here's our original free body diagram. I had these attractive forces from these negative charges. All right, and then my new free body diagram, if I put a charge positive q over here, and I have some positive test charge over here. Oh, what just happened? Give me a second. Yeah, I can go back with this. Okay, so then the positive test charge is going to push away from the charge positive q, but it's still going to be attracted to negative q. And if you see these free body diagrams, right, we understand that the distances stay the same. We just changed the sign of one of the charges. Well, then these two vectors have the same magnitude, it's just in different directions. All right, so describe how the force magnitude you derived in part B and direction of the force on the test charge would be different, if at all. So the force magnitude would be no different because the magnitude of the forces didn't change. And then in terms of the relative angle, that also didn't change. And then the final question is, the direction of the force on the test charge would be different. Justify your response. So here, when we did the net force, all right, I'll draw it in green. We had a net force pointing in the negative y direction. And then here, we're going to have a net force pointing in the positive x direction. Right, and that's the only difference. The magnitude of the forces stay the same. Well, anyways, I hope that was helpful. If you have any other questions, just let me know. And then definitely just review everything, right? So like, especially, I would say the most important problems would be the sphere. So conducting sphere, being able to apply Gauss's law, being able to integrate in non-uniform charge distribution, right? So we're not just looking at point charges. We're looking at spheres, conducting spheres, insulating spheres, rods. It could be, a sheet, a ring of charge, anything, all right? So you have to practice setting up the integrals, right? So look at the example we did here. Look at the examples from the one packet, whichever one, the chapter 12 drills. And then look at the examples from the extra little practice tests I gave you all. And then also don't be afraid to look stuff up online, right? So to practice setting up integrals for these kind of problems. It's very similar to what we did for moment of inertia. So the moment of inertia and then looking at doing center of mass problems, it just takes practice, all right? So anyways, study up this weekend and good luck on the test.